Welcome everyone to this video. Uh, we are going to discuss a question from the book at C Verma. The question is on the chapter of magnetic effects of current or magnetic field due to current. So basically the question is that you have a thin, infinitely big sheet of current carrying conductor. So you have a conductor like this. These are the charges, how current is flowing in the conductor like this. Now there is a conductor just below it in which current is flowing in the opposite direction. Now in such a case where current is flowing through the whole sheet, we define current flowing per unit length, where this is the length which we are talking about. So this current J, this is current flowing per unit length. So just to redraw what the question is, basically we have a charge. Now there would be mag field produced because of this configuration, this J and this J, both they are flowing in opposite directions. There is a current placed in the middle of these two conductors. Question is, if it is projected parallel to the plates, the speed v, and it goes in some kind of circle. So we are given that the radius of circle is r. So what is the speed with which the charged particle of charge q is projected? So this is a very good question where we have to use two concepts. We have to find the mag field due to a new kind of current configuration, and we have to use an earlier concept of moving charges in magnetic field, and use a simple idea that what kind of mag field it's going to be and what is going to be the radius of its circle. So uh, basically in this kind of case where you have a charge conductor, let's say these points, so that the current is coming outside of the conductor, and these points inside where the current is going in. So we can take an Amperian loop like this. Now just like opposite charges, let's say if we had two charges, negative charge and a positive sheet and a negatively charged sheet, in this case you could easily guess that the all the electric field is contained within the sheets only for infinitely large sheet, and no electric field is present outside the sheets. Same case happens here as well. So if you apply the magnetic field the right hand rule, you would find that the direction of magnetic field is like this, or just opposite to it. Actually magnetic field would be in this direction. Magnetic field is in this direction. So when magnetic field is present in this direction, then we can say that magnetic field into L distance, B into L, let's say whatever distance we have taken, would form part of the Amperian loop V dot dl and line integral. Magnetic field everywhere else is 0 except at this particular line. Otherwise B dot dl is 0 at this section and this section. So B into L is simply your J, current flowing in the conductor, into length L, whatever current is flowing through this part of the conductor, into mu naught. So this value would have been halved if there had been a single conductor, but there are two, so that's why the magnetic field is only present at one point. So this magnetic field B is simply J mu naught. With an easy calculation, we can say uh, now if we are to find what is the radius of the circular path, the magnetic field is in this particular direction, as you can see, and the charged particle was projected uh, perpendicular to the magnetic field. So it was projected like this, q charge. So it will go in a circular path like this. It will go in a vertical circle, but still it will go in a circle nonetheless. And we know that R is equal to mv upon qv. This came from the formula that mv square by r, centripetal force, is provided by the magnetic force qvp. So after solving this, we can easily get this, and just substituting the value, we'll get this. So this is the speed with which the charged particle is projected to get a circle of radius r, qj mu naught by m. So hopefully we learned something from this question. Thank you for joining.